Lab 7 Michelson application Owen Litz.
And I'm Richard Pang. This is for our TA Lam Nguyen.
Interferometer calibration. The goal of this part of the experiment was to calibrate the interferometer using the helium neon laser. This was done counting 100 fringe oscillations in the diffraction pattern. The difference in distance that the mirror had to move to cause this was recorded and used to calibrate the calibration factor. The setup is shown on the right.
For theory and results, we know that D source moves less the distance of D mirror, thus delta D source equals 2 delta D mirror equals D source 2 minus D source 1. Plugging this into the equation from the lab procedures, we can find that the calibration factor equals 2 delta D mirror over 100 lambda, because we are counting 100 fringes. In our experiment, we measured that delta D mirror was about 70 microns, and thus plugging this into the equation for calibration factor, we find that calibration factor is 2.244.
Part B, measuring wavelengths of sources. In this part, the wavelengths of 3 different sources, a laser diode, sodium lamp, and a mercury lamp were measured using the properties of the Michelson interferometer. This was done by counting the 50 fringe oscillations while changing the distance between the two mirrors. Here is the setup for part B of the experiment with the mercury lamp on the left, the sodium lamp in the middle, and the laser diode on the right.
Part B theory and results, we can rearrange the equation from part A to find lambda instead of the calibration factor. We find that lambda equals 2 delta D mirror over CF M2 minus M1, where M2 minus N1 is the 50 fringes that we counted, and our calibration factor is 2.244 for all 3 experiments. For our mercury source, we found an experimental wavelength of 516.9 nanometers, giving us a percent error of negative 5.32%. For our sodium lamp, we found a wavelength of 552.6 nanometers, which gives us a percent error of negative 6.23%. For our diode laser, we found a wavelength of 641.7 nanometers, which gives us a percent error of negative 1.28%, which is pretty good.
Part C, measure wavelength separation of the sodium doublet. In this part of the lab, the difference in wavelength between the sodium doublet was determined. This was done by locating a minimum in intensity of the fringe pattern and changing the micrometer position. The pattern in the fringes will increase in intensity and then decrease again. The difference between these 2 points was measured. This is our setup for part C using the sodium lamp.
Part C theory and results, we can find the wavelength separation by delta lambda equals lambda squared over D source, where lambda is average of the sodium doublet length, which is about 589.3 nanometers. We know that D source equals 2 delta D mirror over the calibration factor. Plugging this into the delta lambda equation, we find that delta lambda equals calibration factor times lambda squared over 2 delta D mirror. This is derived from the total intensity of these two wavelengths, where the zeros of the equation are separated by D source equals lambda squared over delta lambda. We can rearrange this to then find delta lambda. We found our 3 null positions with delta D mirror of 0.56 millimeters and 0.621 millimeters. Taking the average gives us delta D mirror of 0.5935 millimeters, which is what we use. We find that delta lambda is 0.6565 nanometers, giving us a percent error of 11.27%.